In this lesson, we're going to look at the quantitative relationships between pressure, volume, temperature, and number of moles, the four factors that affect the physical behavior of gases, by looking at the gas laws. And the specific gas laws we're going to look at are Dalton's law of partial pressures, Boyle's law, Charles's law, Gay-Lussac's law, the combined gas law, and the ideal gas law. For all gas laws, temperature must be done in Kelvin. The Kelvin temperature is directly proportional to the kinetic energy, and so we must do all the gas laws in Kelvin. For the ideal gas law, volume has to be in liters, pressure has to be in atmospheres, amount of moles in Kelvin, all amount in moles. All gas laws must be done in Kelvin. For these laws, the pressure, the volume can be varied units, but all gas laws must be done in the Kelvin temperature. Looking at Dalton's law of partial pressures, Dalton's law of partial pressure states that at constant volume and temperature, the total pressure exerted by a mixture of gases is equal to the sum of the partial pressures of the component gases. Very simple equation. Total pressure is simply the sum of all the pressures making up the mixture of gases. So when you see a problem that looks like this, where you're given a total pressure and a mixture of gases, that should tip you off that it is Dalton's law of partial pressures. So here we have a mixture of oxygen, nitrogen, and argon gases. So the total pressure is going to be the sum of the pressure of the oxygen, nitrogen, and argon. You are then given a total pressure, a pressure of oxygen, a pressure of nitrogen, and you're asked for the pressure of argon. So just substitute in total pressure plus the pressure of the oxygen plus the pressure of nitrogen, and that'll allow you to calculate the pressure of argon by a little bit of simple math. Another way to think of Dalton's law of partial pressures is that the total pressure is equal to the sum of the amount of each gas that is present. In other words, mole fraction is directly proportional to partial pressure. If the mole fraction of oxygen is 0.25, or 1/4 of the mixture is oxygen, and 1/4 of the mixture is nitrogen, and 1/2 of the mixture is hydrogen. If the total pressure is 40, then 1/4 of that 40 is going to be the oxygen, 1/4 of the pressure is going to be the nitrogen, and 1/2 of the pressure is going to be the hydrogen. So partial pressure is directly proportional to the amount of each gas in the mixture of gases. Next three laws, Boyle's, Charles, Gay-Lussac's, we can collectively call them the Guy's gas laws. And for all these gas laws, the number of moles are held constant. And there's a little device here. If you can imagine a card with PTV, note the alphabetical order on that. And that is excluding moles because moles are held constant for each of these. And with this device, we can describe the relationship between these three variables for Boyle's, Charles, and Gay-Lussac's law. Let's look at Boyle's law first. If you could imagine pinning the T to a corkboard. So imagine a card pinned to a corkboard so that the T cannot move. And if the temperature and number of moles are constant, we can answer the question, how do the pressure and volume change with each other? If the T is pinned and pressure goes down, then the card is going to rotate so that the volume is going to go upward. In other words, as one goes down, the other must go up, and vice versa. If the pressure were to go up, then the volume must go down. So that shows an inverse relationship. In an inverse relationship, a constant, let's call it K, is equal to the product of the two variables involved. Again, K is a constant. If we were to keep that value the same, and if we were to double the amount of P, we would have to cut the V in half so that the product equals the same. In other words, as one increases, the other must proportionately decrease. Let's take a look at Charles's law. In Charles's law, pressure is held constant, on a fixed number of moles. And so it's going to describe how temperature and volume are going to change with each other. If the P is pinned and the T goes up, then the V must also necessarily go up. So this shows a direct relationship. In other words, K is going to equal the volume divided by the temperature. If we double the volume, we also have to double the Kelvin temperature to keep it equal to K. And so again, as one increases, the other one must also increase proportionately. And for Gay-Lussac's law, now we're going to hold volume constant and ask, how do pressure and temperature then vary with each other? So if the volume is held constant, if T goes up, P must also go up. If P goes down, T must also go down. In other words, this is also a direct relationship. K then is going to equal P divided by T. And if we cut P in half to keep it equal, T must also be cut in half. So the two must vary directly with each other. Taking a look at a Boyle's law sample, or Boyle's law states that for a given mass of a gas at constant temperature, the volume of the gas varies inversely with the pressure. So again, we see the product of the two variables showing an inverse relationship. Typical Boyle's law problem looks like this. Note temperature is constant. Remember, water boiling is a constant temperature, to help you remember that. And it's really just a matter of plug and chug. Here we're given a V1 and a P1 and a P2, and we're asked for a V2. So it's just a matter of plugging in. P1 is given as 0.78 atmospheres. V1 is given as 400 liters. P2 is 0.98 atmosphere. It's changed to 0.98, so that is P2, not P1. And we're asked to solve for V2. And a little bit of math there is going to give us 318 liters. Rounding to two significant figures will make that 320 liters. Charles's law says the volume of a fixed mass of gas, indicating again N is constant and pressure is constant. So again, this is going to describe the relationship between volume and temperature. The constants, the N and P, do not show up in the equation. And so being a direct relationship, V1 is to T1 as V2 is to T2. Again, pressure being held constant. If one goes up, the other must also go up. Sample problem. Here we have our V1 at a T1, and then we're given a T2, and we're asked for a V2. So we want to solve for V2 given V1, T1, T2. Substituting in, solving will give us 2.1 liters. Gay-Lussac's law says the pressure of a fixed mass of gas, so again, N is constant and volume is going to be constant. And so these are not going to show up. And what Gay-Lussac's law says, when volume is constant, the pressure and temperature vary directly with each other. So P1 over T1 equals P2 over T2. Sample problem. Here we're given a volume, but that volume is constant, so we can pretty much ignore this in this problem. So here is a T1, here is a P1, a P2, and we want to solve for a T2. What will the final temperature be? And so P1 over T1 equals P2 over T2. This problem gives us the temperature is 27 degrees Celsius. Again, we cannot do gas laws in Celsius. We must convert to Kelvin. To convert Celsius to Kelvin, you will add 273. So that gives us our T1 as 300 Kelvin. And then again, we have to solve for T2 in this problem. So cross multiplying, dividing gives us a T2 value of 144 Kelvin. Or again, reducing to 2 sig figs, that would be 140 Kelvin. This one is the combined gas law. If we look at the numbers given, we are given a V1, we are given a T1, and a P1, and then we see the pressure being changed, so that is a P2 and a T2, and we're asked for a V2. In other words, both the pressure and the volume and the temperature are all changing. And so this is the combined gas law equation. It shows an inverse relationship of pressure and volume. It shows a direct relationship between pressure and temperature and a direct relationship between volume and temperature. If you want to simplify this equation, you can cross multiply first, giving you this form of the combined gas law. And then you can simply substitute in the problem's values given. We want to solve for V2 in this particular problem. Note the temperatures are converted to Kelvin. This is our T1. We add 200, well, it's our T2. So we add 273 to get our T2. And we add 273 to get our T1. Pressure can be left in millimeters of mercury, and volume can be left in milliliters for this problem, giving us a final answer of 75.3 milliliters. For this problem, note that we are given moles. The only gas law that allows you to calculate moles is the ideal gas law, where pressure times volume equals number of moles times the ideal gas constant times the temperature. R is the ideal gas constant. It's a proportionality constant between the product of the pressure and the volume and the number of moles and the temperature. It is equivalent to 0.0821, typo there, so 0.0821 liters times atmospheres over Kelvin times moles. And so since these are the units for R, and R is in our problem, then we see that volume must be in liters, pressure must be in atmospheres, like all gas laws, temperature must be in Kelvin, amount must be in moles. So we're given pressure as 1,193 millimeters of mercury. We must convert that to atmospheres by dividing by 760. So that gives us a pressure of 1.57 atmospheres. Volume is given as 7,240 milliliters. Dividing by 1,000 is going to give us 7.24 liters. And temperature, again, always must be converted to Kelvin by adding 273. That is going to give us 295 Kelvin. And that'll come out to 0.469 moles. All these units being converted gives us cancellation between atmospheres and atmospheres, liters and liters, kelvins and kelvins. That leaves us with moles, which is what we are solving for in this particular problem. So the units of R really do confine us to certain units in the ideal gas law. One more sample problem. Again, this is 0.0821. In this problem, we're given a volume of 550 or 5.50 times 10 to the fourth milliliters. By dividing by 1,000, we can calculate that as 55.0 liters. So that is our volume. We're given an amount of gas of 131.84 grams of oxygen. That has to be converted into moles, so we divide by the molar mass of the diatomic oxygen gas to get the number of moles present. We're given the pressure as millimeters of mercury, and again we've got to convert that to atmospheres. And so now that we've converted all to our correct units, now liters and liters will cancel, atmospheres and atmospheres will cancel, moles and moles will cancel, leaving us kelvins, which is what we are solving for in this problem. We algebraically rearrange the ideal gas law to get temperature. We get that equation, and the final answer here comes out to 813 Kelvin.